Hello everyone, welcome to the first tutorial in our machine learning course, and in this tutorial we are going to see how to implement simple linear regression using Python. Before going for actual implementation, let us go through few important concepts related to linear regression. In fact, we have gone through these concepts earlier, but still let us have a recap of those concepts. For detailed discussion of linear regression, I would suggest all of you to once again refer to the videos uploaded on the YouTube. So the links of the videos are being provided in the description. So please refer to these videos for detailed theoretical discussion related to linear regression. So let's begin with the concept of simple linear regression. Regression is a problem under supervised learning. So we have been provided with some training data, and this training data is of the form x, y, where x is a single feature describing the example and y is the continuous value output. So as we are discussing simple linear regression, please note that we are having only one feature describing the example. So this single feature x is known as independent variable, and we are having the output associated, or we would like to predict some value for the output, and that is actually the dependent variable y. So we are being provided with the data samples like this, wherein we are having the x value along with the y value in our training data set. And what we are supposed to find is, we need to find a line or a hypothesis of the form h theta x equal to theta 0 plus theta 1 x, which best fits the data points, providing the least square error. Okay, so given the data points are being described with a single feature, and that is why this is simple linear regression, and we are supposed to come up with a line or a hypothesis of the form h theta x equal to theta 0 plus theta 1 x, right? And we are supposed to find out such kind of a linear regression line that is providing us the least squared error. So idea is to choose this theta 0 and theta 1 parameters so that our h theta x is close to y for our training example of the form x, y. Okay, so in linear regression, let us see how to compute an error. Okay, so for given sample xi, we are having the actual output yi. Okay, so this superscript I denotes the sample number. So if I am having m number of samples, I will be having the data provided of the form xi, yi. So I denotes the ith sample. So I will be having some value of x associated with the ith sample, and also we are knowing the value y, output value y for the ith sample. So for given xi, the actual output is yi, and using the regression line for some value of theta 0 and theta 1, we are predicting the output as theta 0 plus theta 1 xi, right? So error for xi is given as our predicted yi minus actual yi, right? So error for the sample xi is denoted as predicted yi minus actual yi. Okay, so here our predicted yi is nothing but theta 0 plus theta 1 xi, and we are knowing the actual yi value. So this difference theta 0 plus theta 1 xi minus yi is actually giving us the error for ith sample. Okay, so in other way we may write this error like h theta xi minus yi. Okay, fine. Now let us look at how we are going to define the error for m number of samples. So this is how we are going to compute the sum of squared error. So this is the error for ith sample, h theta xi minus yi, right? So we are squaring this error, okay, and we are having m number of samples, so we are having sum of squared error. So this is my squared error for ith sample. We are having m number of samples, so we are having summation over all those m samples, and we are actually going to find out the mean of this sum of squared error. So we are having here the multiplier 1 divided by m. In fact, instead of 1 divided by m, we are having here 1 divided by 2m. And why we are having this 1 divided by 2m? The reason is for some mathematical convenience, that's all. Okay, now as I stated, m is the number of data points or size of our training data. And what is our goal? Our goal is to find theta such that error is minimum. So look at this figure. So if these are the data samples, right, and if this denotes our regression line, then what we mean by this error, associated with every sample, this vertical line indicates the error. Okay, so I am having some actual y value, and using this hypothesis for some x, I will be having some another y value. So y predicted value and y actual value. So the difference between y predicted and y actual is nothing but the error with respect to that sample. So this is how we are going to compute the errors. So this is the error h theta xi minus yi. We are squaring that error. We are having the sum of squared error, right? And then we are finding out the mean. So ultimately what we need to do is we need to come up with this hypothesis h theta x such that the theta values are providing us the minimum error. Okay, so find out the parameters theta 0 and theta 1 to minimize our objective function, and this is nothing but learning. And this j of theta 0 theta 1 is known as the objective function or the cost function. Okay, fine. Now let us summarize the expressions those we have. The hypothesis is h theta x equal to theta 0 plus theta 1x. The parameters are theta 0 and theta 1. The cost function is j of theta 0 theta 1 equal to 1 divided by 2m summation over I equal to 1 to m h theta xi minus yi square. And our goal is to minimize the cost function j of theta 0 theta 1 to come up with the optimal values of theta 0 theta 1. So whenever we reach to the minimum cost function j theta 0 theta 1, whatever are the respective theta 0 theta 1 values, those we would like to find. Okay, so this is our problem. Now to minimize this cost function j of theta 0 theta 1, we are making use of gradient descent algorithm. So what is gradient descent algorithm? We are having here the algorithm wherein we are saying we are repeating a step that updates the values of the parameters theta j. So repeat until convergence theta j equal to theta j minus alpha into the partial derivative of the cost function j theta 0 theta 1, and we are going to update the thetas for j equal to 0 and j equal to 1, as we are having two parameters theta 0 and theta 1. So in every iteration we are going to update the value of theta 0 as well as the value of theta 1. Okay, now this alpha is known as the learning rate, and this partial derivative is also there, and this partial derivative is multiplied with this learning rate. Okay, now please note that we need to update these thetas or the parameters simultaneously. Okay, so here is how we are going to perform this simultaneous update. So the correct implementation is actually the simultaneous update. So how we are going to update those parameters? So we are updating the parameter theta 0 with this expression theta 0 minus alpha into the partial derivative of j with respect to theta 0, whereas theta 1 gets updated with the expression theta 1 minus alpha into partial derivative of j with respect to theta 1. So what we are going to do is we are going to have two temporary variables, temp 0 and temp 1, and those are actually storing the new values for theta 0 and theta 1, and after storing these new values to be updated, then we are going to update theta 0 and theta 1 simultaneously. So theta 0 is updated, theta 0 is assigned the value of temp 0 and theta 1 is assigned the value of temp 1. So this is the correct implementation, and that is known as the simultaneous update. Whereas in incorrect implementation, sometimes the people get confused while updating those parameters, and what they do is they compute temp 0, right, by computing the update value for theta 0, and then they immediately assign temp 0 to theta 0. So they immediately update theta 0, then computation of temp 1, and then updation of theta 1. But why we are saying that this is incorrect implementation? Because whenever we are computing here temp 1, right, we are computing the partial derivative of j of theta 0 theta 1 with respect to theta 1. So while computing this partial derivative, what we need is we need to use the same value of theta 0 that was used for computation of partial derivative of j with respect to theta 0 earlier, right? But as we have updated this theta 0 value before computing this partial derivative with respect to theta 1, right, the theta 0 that is used here is the updated value and not the original one, and that is why this kind of implementation is incorrect implementation, and this is not the simultaneous update. Okay, fine. So this is incorrect implementation, and we should always go for the simultaneous update in this way to update the parameters. Okay, fine. So let's proceed now how gradient descent algorithm is being used for linear regression to minimize the cost function j. Now whenever we apply gradient descent algorithm for linear regression, our algorithm will become like this. So repeat until convergence, theta 0 gets updated as theta 0 minus alpha into 1 divided by m summation over I equal to 1 to m h theta xi minus yi, theta 1 equal to theta 1 minus alpha into 1 divided by m summation over I equal to 1 to m h theta xi minus yi into xi, where this is my partial derivative of j of theta 0 theta 1 with respect to theta 0, and this term denotes the partial derivative of cost function j with respect to theta 1, right. So in fact, for coming up with this theta 0 theta 1, we need to implement this algorithm for updating theta 0 theta 1, right. So we are making use of gradient descent to come up with the optimal values of theta 0 theta 1, and whenever we get optimal values of theta 0 theta 1, we are getting a least regression line with the hypothesis h theta x equal to theta 0 plus theta 1 x, okay. And please note here, we need to update theta 0 and theta 1 simultaneously, right. Fine. Now, as I mentioned earlier in this slide, see here how we should implement this simultaneous update. Temp 0 is computed as theta 0 minus alpha into this term 1 divided by m summation over I equal to 1 to m h theta xi minus yi, and temp 1 is computed as theta 1 minus alpha into 1 divided by m summation over I equal to 1 to m h theta xi minus yi into xi, and then simultaneously we are going to update theta 0 and theta 1, right. Fine. So this actually we are going to implement practically this algorithm of linear regression using gradient descent, okay. Fine. Now, as far as practical implementation of simple linear regression is considered, we are making use of a programming language Python, okay. So Python is a popular object-oriented programming language having the capabilities of high-level programming language, and Python was developed by Guido van Rossum at Stichting Mathematics Centrum in Netherlands. Its first version was released in 1991, and it is an open source programming language, which means that we can freely download it and use it to develop programs. So the Python can be downloaded from this website, official website of the Python, www.python.org, and I would recommend you to install Python if you are not having Python installed in your system. Now, while writing the code for the simple linear regression in Python, we need to make use of few of the libraries, and here I am going to just mention which libraries we are going to make use of, okay. So, and also I am mentioning here why in fact the Python is being used for machine learning applications. So there are certain features those actually make Python as the very important language to be used for building machine learning applications. So the very first feature is the extensive set of packages. So Python has extensive and powerful set of packages which are ready to be used in various domains. So few of such packages are like Numpy, SciPy, pandas, scikit-learn and so on. So these packages are really very helpful to implement certain functionalities while writing the code in Python, okay. Further, Python is suitable for easy prototyping, right. So this is one more important feature of Python that makes it the choice of language for data science and machine learning, okay. It becomes very easy and it is a fast approach towards prototyping. Okay, next, collaboration feature. So the field of data science basically needs good collaboration, and Python provides many useful tools for such kind of a collaboration. A typical machine learning or data science project includes various domains like data extraction, data manipulation, data analysis, feature extraction, modeling, evaluation, deployment, and updating the solution. As Python is a multi-purpose language, it allows the data scientist or the machine learning enthusiast to address all these domains from a common platform. And these are various advantages why Python is being used for building machine learning or data science applications. So now let us go through few of the libraries those we are making use of while implementation of simple linear regression. The first library that we are going to use is Numpy. So Numpy is a library for the Python programming, adding support for large multi-dimensional arrays and matrices along with a large collection of high-level mathematical functions to operate on these arrays. So while implementing the applications, many times we need to make use of many high-level mathematical functions, and also we need to use or operate upon the arrays and matrices. So Numpy is a library that provides all such kinds of functionalities. Okay, so we are going to make use of Numpy. The next library that we are going to make use of is the matplotlib. So matplotlib is a plotting library for the Python programming language and also its numerical mathematical extension Numpy. It provides an object-oriented API for embedding plots into applications for visualizing the data. The next library that we are making use of is pandas. So pandas is a software library written for the Python programming language for data manipulation and analysis. Specifically, it offers data structures and operations for manipulating numerical tables and time series. So it is a free software released under the BSD license. So pandas is a library freely available to be used with Python. So with this, we are going to see now the actual practical implementation for our simple linear regression. Okay, so let's proceed now for the implementation. So let us go to the practical implementation of simple linear regression. So let me open the code. I have written the code for simple linear regression. Let me open that code and then I'll be demonstrating you how that code is written, what is the significance of every statement that is written in the code. Okay, so that you can understand how the simple linear regression is being implemented. And here we go. So this is the code that demonstrates simple linear regression, and we are making use of gradient descent, right, to minimize our cost function. So we are writing the simple linear regression from scratch. Okay, now while writing this Python code, the very essential first step is to import the packages. So as I mentioned earlier, we are making use of three packages: Numpy, pandas and matplotlib. So here are the statements: import Numpy as NP. So Numpy, as I stated earlier, Numpy helps us to make use of arrays, matrices and the mathematical functions. So various functions are available in Numpy those can be used, right, to deal with arrays matrices and to compute some mathematical quantities. The next library that we are making use of is pandas. So we are importing pandas, and this is the statement: import pandas as PD. So this pandas library is meant for data manipulation and analysis. Next, we are making use of matplotlib. So we are writing here the statement: import matplotlib.pyplot as PLT. So matplotlib is the plotting library, and this will help us to visualize the data by drawing certain plots. Okay, now the next statement, we are using this matplotlib function plt.rc parameters figure size equal to 6.0 comma 4.0. So what this statement is doing, in fact we would like to visualize the plots. So to visualize the plot, what would be the size of my figure? So that size of the figure is being mentioned here, 6 by 4. Okay, fine. Now after importing the required libraries, what next? We want to read the data, right? So as I stated, we are implementing linear regression for single variable, or we are having only one feature. So here we are making use of one data set available in the public domain, and that data set is the salary data set. So what we have in this data set, we are having the experience of the person as the feature, and based on that feature the output is the salary of the person. Okay, so X is the experience of the person and Y is the salary of the person. So let me show you this data. Okay, so we are having this salary data set. So this is a very simple data set, and we are having only 29 samples or observations in this data set. So if you look at every line in this data set is having two values, and those are separated with commas, right? So 1.1 is the number of years of experience of a person, and this second figure is the salary that person is drawing. Okay, so the first value or the first quantity is my X, that is the years experience in years, and the second quantity is the salary. And in my training data set, we are having here 29 examples or 29 samples, or we are having the data related with 29 persons or employees. So the data is having the years of experience along with salary. So X input is years, or the experience in years is my input X, and the output Y is the salary that we would like to predict. Okay, fine. So this is how our data looks like, and we are making use of this data set, right, for training. Okay, so let's once again go back to our program. So what we are doing here is we are using a function from the pandas library. So which function we are using? readcsv. So our data is stored in this file salary dataset.csv. So CSV is comma separated values. CSV stands for comma separated values. So I have shown you how our data file looks like. Okay, so we would like to read the data from that file and that is why we are making use of this function read_csv. So this function returns a data frame, and this data frame is stored in this variable data. Okay, now what we have in this data frame? In this data frame we are having all the data that we have read from this salary dataset.csv file. Okay, now as we are having the entire data in this data frame data, what we would like to do is we would like to separate out our x and our y. So we want to separate out our feature values and we would like to separate out the output. So input is denoted here as x and output is denoted here as y. So how we are going to separate out this x and y from the data frame? We are making use of this function ILOC. So what this colon indicates? This colon indicates that we would like to extract all the rows from this data frame and the 0th column. So we are having here the column indices beginning from 0. So whatever is the first data column, right? Once again I'll show you the data file. So see here, this 1.1 is my x value for first sample. This 1.3 is x value for second sample, and so on. And similarly this 39343 is y value for first sample, 46205 is the y value for second sample, and so on. So whenever we are making use of this statement read CSV, what happens is this entire file is read. Okay, and this data is being stored in this variable data. And what we would like to do is we would like to separate out all x values and all y values. So simply what we are doing is we are making use of that data frame data with the functionality available iloc, and in the square brackets we are writing what we would like to extract from this data frame. So this colon indicates all rows and this 0 indicates 0th column. So here this x value represents the 0th column and this y value represents the first column. Okay, so from all rows this 0th column is being extracted and stored as x, whereas all rows and this first column is being extracted and stored as y. Okay, fine. Now after this we are going to look at our data. So we want to plot how our data looks like. We are going to plot how our data looks like, and that is why we are making use of this scatter plot. So we are writing the statement plt.scatter because we would like to use a scatter plot x comma y. So in x we are having all x values, all data points or all x values of the data points, and in y we are having associated output values y. So x is my independent variable and y is my dependent variable. Okay, so I'll be giving the labels for x axis as x and y axis label is y, and for this plot I am providing the title as training data, and this plt.show will actually show me the plot. Okay, so let us do this. Let me show you the output of this code. So I have commented out all rest of the code, and let us see the output of this particular code. Okay. So simply these many lines are there in our code now. So let me run this code. And see here what we are visualizing. So see here what we have done and what we are visualizing here. So we have imported the libraries, we have fixed this window size to depict our plots. Okay, so this is my figure size 6x4. Now we have read the data from the CSV file. We are having now this x and y separated out, and then we are making use of this scatter plot, right? So scatter is a function from matplotlib pyplot. Okay, so scatter function is being used to visualize this data. So the first data point, the second data point, and so on. So all those data points are being plotted. So on x-axis we are having x, and here we are having y. So x is our experience in years, and on y we are having the salary. So now we have plotted this data, training data, just to visualize the observations, how these observations are spread in this space. Okay, now let's close this and let's go back to our program. So let us remove the comments from the code and let us proceed with the next steps. So now we have read the data and we would like to build our regression model. So while building the model, we need to create, or we need to come up with a function h of x equal to theta 0 plus theta 1 into x. So this is what our hypothesis is, and we would like to come up with this hypothesis. Okay, so these are the parameters theta 0 and theta 1. So we are going to initialize those parameters to 0. Okay, so we are making, or rather we are using the gradient descent algorithm to implement this linear regression, and whatever are those parameter values, we are initializing those parameters to zeros. Okay, so theta 0 is the parameter 0, theta 1 is the parameter which is initialized to 0. Now in our cost function we are having the cost function. So let me show you our cost function. So just see here, our cost function is j of theta 0 theta 1 equal to 1 divided by 2m summation over I equal to 1 to m h theta xi minus yi square. Okay, so this is our cost function, and now whenever we want to minimize this cost function using gradient descent, what we are going to do is we are going to use this gradient descent algorithm for linear regression. So here the parameters theta 0 and theta 1 are being updated, and how these are updated, we are having this alpha, that is the learning rate. So we need to initialize, or we need to fix some value for this learning rate also, alpha, and this is the derivative term actually. So this is our partial derivative of cost function j with respect to theta 0, and this is the derivative of the cost function j with respect to theta 1, and these same expressions we are going to implement in our code. Okay, so see here, alpha is being initialized. Alpha is our learning rate and we are initializing that alpha equal to 0.01. Okay, so we have initialized this alpha as 0.01. Okay, now what next? We want to find out how many examples we have in our training data set. So we are having here a statement m equal to length of x. Length of x. So what is this x? X is storing my input values. X is storing my input values. So x is storing all those values in column 0 of my data frame. Okay, so just I want to find out how many samples are there. So I am making use of this function length of x. So length of x will give me the number of elements in x. Okay, and this number of elements in x is nothing but the number of observations in the data set. Fine. So this is how I am getting this value m, number of examples or number of observations. The next value that I am initializing is the threshold for auto convergence. Okay, so we have seen earlier the concept of auto convergence. So we are having some threshold epsilon, okay, to determine whether we have reached to the minimum, global minimum. Okay, so here we are having this epsilon value set to 0.0001, a small number. So epsilon is a very small number that we would like to have. So this is a threshold for auto convergence. Okay, now what next? We are having one more variable here, cost old. So this variable is actually storing the cost in earlier iteration. So we are going to find out the difference in the cost value. What was the cost? Cost is nothing but the error. So what was the cost in the earlier iteration and what is the cost in the current iteration, right? So that difference we would like to find out, and that is why it is important to store the cost or the error for the previous iteration as well. And to store that, we are making use of this variable cost old, and we have initialized some value for this variable as well. Okay, as I stated, we want to find out the difference in the error, okay, or difference in the cost value of the earlier iteration and the next iteration, and that is why this is the variable that we are going to make use of to store this difference. And this iterations is the variable that we are making use of to compute the number of iterations those are required to converge, okay, to come up with the hypothesis. Okay, because we are using auto convergence, and that is why we want to see how many iterations are required to reach to the convergence. Okay, fine. Now let us see how we are performing gradient descent. So we are having here the loop. So in our algorithm we have mentioned that repeat until convergence. So this is the iterative functionality, or this is a while loop where we are going to iterate some steps. So repeat until convergence. So what is the convergence condition here? The convergence condition is mentioned like this: absolute difference should be greater than epsilon. Epsilon is a very small threshold that we have decided when to stop. Okay, so when we are going to stop and when we are going to iterate, so we are going to iterate if the cost difference in the earlier iteration and in the current iteration is greater than this threshold epsilon. So if cost is significant, if cost is more than this value of epsilon, then we would like to iterate. Otherwise, we are going to stop. Okay, so this is our convergence condition. Now, what next we are going to do is, we are going to compute the y prediction. So, we want to find out the predicted value. Okay, y prediction. So, let us once again go back here. Okay, so what is my y prediction? My y prediction is, in fact, the value that is being provided by this hypothesis, h theta x equal to theta 0 plus theta 1 x. So whatever my hypothesis is giving me for a particular value of theta 0 and a particular value of theta 1 for the sample x is my predicted value, and this predicted value actually we are going to find out. So y prediction, that is my hypothesis, right? So how I am going to compute the hypothesis value? Theta 1 x plus theta 0. Theta 1 x plus theta 0. Now please note here that this x is a matrix, or rather it is a column vector, wherein I am having all the x values associated with our samples in the data set. So x is not a singular value, x is not a single value, but x is set of values, right? And what we are doing by making this simple one statement, what we are doing is, for all the x values, so all x values means this 1.1, 1.3, 1.5 and so on. So we are having 29 samples. So all those 29 x values are stored in this x. Okay. So at one go, using this one single statement, we are manipulating all the values those are stored in x, and we are going to predict the values y predict. So once again, this y predict will have the size that is same as x. So number of examples is the size of x. So y predict will also have the size that is similar to that of x, number of examples that we have. Okay. So for whatever is the theta 1 and theta 0 values, those are selected, right? We are going to compute the predicted values for all those samples x. Okay. Now whenever we have initialized our theta 0 and theta 1 values to 0, in the first iteration, in the very first iteration, I will be having this theta 1 equal to 0 and theta 0 equal to 0. So obviously I will be getting y predict value equal to 0. Okay. But as we go on iterating, in every iteration we are going to update these values of theta 0 and theta 1. So in the next iteration, whatever may be my theta 1, theta 0 values, we are going to predict the output for all training examples, right? And this is how we are going to proceed. So in this step, what we are trying to do is, we are computing the y prediction values for all input values x. Now we are having now all these 29 values computed for y prediction. Now we are going to compute the cost. So how we are going to compute this cost? We are going to compute this cost with our cost function, that is half into or 1 divided by 2m into sum of y prediction minus y square. So see now this function, what this function is doing. What we want to compute the error, right? Compute the error for all the samples, right? So in y I am having the actual values. In y I am having the actual values. So these values, these salaries for every input. So y stores all those salary values, actual salary. And what this y prediction is giving me? This y prediction is giving me the predicted salaries for all x's, and those predicted salaries we have computed with this expression or this statement. Okay, so I know the predicted value, I know the actual value. So difference in predicted value and the actual value, this star 2 meaning the square of this error. So square of this error, and we are having sum of square. So this y predict and y are of size equal to number of examples. So with this statement, with this single statement, we are computing the squared error for each sample, and with this sum function we are computing sum of squared error, right? We are computing the sum of squared error, right? So sum of squared error multiplied by 1 divided by 2m. So this is how we are going to compute our cost function j of theta 0 theta 1, j of theta 0 theta 1. Okay, so this j of theta 0 theta 1 is computed and stored in this cost, this variable cost. Okay, now we have computed the cost. Now what next? We want to simultaneously update now the parameters. So to update the parameters, let us once again go to our formula for gradient descent with linear regression. So see here, yes, so this is our gradient descent algorithm for linear regression. Okay, so what we have now computed the cost. Okay, and after computing the cost, we are supposed to compute this derivative, and also we need to compute this derivative. Okay, so this h theta xi is nothing but our predicted value, and yi is our actual value. So predicted value minus actual value, summation of all those differences for all m samples multiplied with 1 divided by m. So this is the derivative with respect to theta 0, and the same thing multiplied with xi, this would be the derivative with respect to theta 1. So how we are going to compute these derivatives? So see here what we have done. So this d theta 1 is the derivative with respect to theta 1. This d theta 1 is the derivative with respect to theta 1. So how we are going to compute this derivative with respect to theta 1? See here, we are having derivative with respect to theta 1, this term. So this we need to compute. So how we are going to write it in code? Okay, so see here what we have written, 1 divided by m, 1 divided by m into this summation. Okay, so summation prediction minus actual into x. Okay, so the same thing we have written in the code. So 1 divided by n into sum of x into y prediction minus y. Okay, so please note here, once again I am emphasizing, please note here, y prediction x, y are not the single values, but these are the set of values, and these statements are actually giving us, or these statements are operating upon the entire set at a time. So at a time we'll be getting, right, this sum multiplied with 1 divided by n. So this is derivative with respect to theta 1. Similarly, the derivative with respect to theta 0 is being computed as 1 divided by m into sum of y prediction minus y, right. So this is equivalent to whatever we have mentioned in this slide. So this is the derivative with respect to theta 0. So this is y prediction minus y. Okay, summation of all into 1 divided by m. The same thing we have written here, y prediction minus y, summation of all into 1 divided by m. So this is derivative with respect to theta 0. What next? Now here comes the simultaneous update. So we have computed the derivatives with respect to theta 1, derivative with respect to theta 0, and now we are going to update our theta 1 and theta 0s. Okay, so how we are going to update this theta 1 and how we are going to update this theta 0? So theta 1 is updated as theta 1 minus learning rate alpha into d theta 1. Theta 0 is updated as old theta 0 minus alpha, that is the learning rate, into the derivative with respect to theta 0. Right. So once again let me show you how we have updated. Theta 0 is updated as theta 0 old value minus alpha into derivative. Theta 1 is updated as theta 1 minus learning rate into derivative. So the same thing we have written here, theta 1, theta is updated as theta 1 minus alpha into derivative. Theta 0 gets updated as theta 0 minus alpha into derivative with respect to theta 0. Okay, now here we are computing now the difference in the cost. So whatever is the old cost and whatever is the new cost. So this cost is the cost in my current iteration, and cost old is the variable that is holding the value of the cost in the earlier iteration. So we are finding out this difference, and this difference is being used to check my limiting condition here, or the convergence condition. Okay, now this cost old, so after computing this difference, the current cost is assigned to cost old, because in the next iteration this current cost is the old cost and new cost will be computed in the next iteration. Okay, so this current cost is being assigned now to cost old. Okay, and simply we are incrementing this count of iterations because we want to see how many iterations are being completed. Okay, or how many iterations we require to converge, and that is why simply we are counting the number of iterations over here. So this loop actually is giving us the optimal values of theta 0 and theta 1. So only just look at how many lines we have written. Hardly 10 lines of code is written for finding out the gradient descent, or to minimize our cost function for linear regression. And after execution of this while loop, right, we are getting the values of theta 0 and theta 1 for which our cost is minimum. Okay, fine. And here we are making use of auto convergence, and auto convergence is I have mentioned earlier that in auto convergence what we are doing is, see for example, here we are having number of iterations and here we are having the cost, then we will have a plot like this, or rather we will have a plot of number of iterations versus the cost function, right? So initially my cost would be high as the number of iterations are increasing, right? I am going to update my theta 0, theta 1 values, and my cost function will go on decreasing, and whenever I reach to the convergence, the difference in the cost of the earlier iteration and the next iteration is very negligible cost or negligible difference. So it is almost flattened out whenever at the time of convergence, and that is why we have mentioned the condition for the convergence: the cost in the earlier iteration and the cost in the next iteration. If the difference is very small, epsilon, then we say that we have converged. Okay, so after executing this particular loop, while loop, we are iterating through, and at the end we will be getting the theta 0 and theta 1 values. So this print statement is printing the number of iterations required, okay, and here this print statement is printing the theta 0 and theta 1 values, those we have got. Okay, now what next? Earlier we have plotted the points in our data set with this, okay, and now using this scatter plot we are plotting our data set, but also we are plotting the line. Okay, that is actually giving me the best hypothesis that I may have. Okay, fine. So I am plotting this line here with these many statements, and after that I am going to predict for the unknown test sample. So I will be providing the experience in years, and using my hypothesis, the theta 0 and theta 1 values, I will be computing the prediction, okay, or the sample. So this is how we have written the code. Now let me execute this code for you. So this is our initial plot, training data is plotted. So experience in years against salary, that we have plotted. Okay, fine. Now see here, my gradient descent has executed, and now just look at this. After coming out from this while loop, I may find out the number of iterations those are required. So the number of iterations required are 5501, 5501 iterations are required to converge this algorithm. Okay, and the theta 0 and theta 1 values for my hypothesis are like this: 25333.95 and theta 1 is 9513.95. So these are the values for my theta 0, theta 1 parameters. So my hypothesis is now h theta x equal to theta 0, that is 25333.95, plus theta 1 x, 9513x. So this would be my hypothesis that I am coming up with. Okay, so this is the hypothesis and this is the line fit. Okay, so these lines are actually plotting the hypothesis that we have come up with. Okay, Now if this is my hypothesis and if I give some value for x, using this hypothesis it should be possible for me to predict the salary. Okay, so the same thing is being written over here. If this is our hypothesis and if I provide the test sample with the experience in year as 1.2, then this y predict equal to theta 1 into test x plus theta 0. So this hypothesis is giving me, so here theta 1 theta 0 values are the theta 0 theta 1 values, those we have come up with. So these values are being used to compute y predicted value for my test sample. So if I provide any unknown test value, it is possible for me to predict it. Okay, so let us see for 1.2. So for this value 1.2, that is the experience in years, we are predicting the salary as 36,750, right? So this is how our algorithm works. Now let me show you simply if we write, or if in every iteration we try to plot our hypothesis. I just want to show you how the hypothesis get changed, or how theta 0 theta 1 values are changed and the hypothesis is being changed in every iteration. Okay, so let me show you in every iteration how our plot looks like for few iterations. So let us run this code once again. So this is my initial data points. So this is the initial value of theta 0 theta 1 0. So this is my initial hypothesis. Okay, and in every iteration, see here how the hypothesis is changing its position as we are changing the values of theta 0 and theta 1. Okay, so this is just to let you understand what actually is happening, right, and how these theta 0 and theta 1 values are being changed in every iteration, and based on these values how our hypothesis is different in every iteration, and the number of iterations required are, just we mentioned 5,000 something, 5,500. So those many iterations are required to fit this hypothesis. Okay, fine. So let me interrupt execution of this code. Okay, fine. So I hope you must have understood how we have written this code. So the heart of this code is this gradient descent. Okay, these many statements. Fine. Okay, so I hope you must have understood. If you have any doubt, please let me know or report me if you have not understood any particular step. Okay, fine. So that's all with the tutorial for simple linear regression. Okay, thank you.